units we're going to be covering. We completed this unit, okay, where we talked about number systems, ASCII, some Unicode conversions, introduced resistors, Ohm's law, and some very basic 1, 2, 3 resistor circuits. And we very briefly talked about binary arithmetic. It will come back down here a little further here, implementing arithmetic. And talked about negative numbers using 2's complement, writing numbers with fixed point binary, which was kind of introductory to being able to do the floating point binary later. And we've talked about diodes. Who remembers what the forward voltage drop across a diode is if I don't give you a number? But turn your mic on and tell me.
0.7.
That's exactly right. 0.7 volts for a regular diode. Now, if it were a germanium diode, it would be 0.3 volts, but we're not going to deal with any of those. The other thing is that LEDs, light emitting diodes, what is the design VF for that guy? Somebody else answer. Can't do the problems if you don't have these numbers memorized, or at least quickly referenceable in your notes.
Would that be 2.1 volts?
Right, 2.1 volts. So the thing we know about diodes is they can go in only one way and have current flow through them correctly. And if it's a regular diode, when it's forward biased, it's going to have 0.7 volts across it. When it is reverse biased, it'll have whatever the power supply voltage across it because no current will be passing through it. If that diode happens to be a light emitting diode, the range is a little different. It starts at 2.1 volts when we're forward biased, and of course it'll have something else across it if it's in reverse bias because the light won't be on. And those are some numbers that we have basically learned to know and love. We also, with resistors, learned some Ohm's law stuff, as you recall, where we said the voltage in across a particular item is equal to the current through that item times the resistance of that item in ohms. And we also learned that the power in watts is equal to the current times the voltage. So we're able to make those calculations based on some things we did either the first or second night. Now, even though this says circuits, diodes, transistor, I always get a little behind on those, but I've made some catch-up time down here a little further to make sure we thoroughly understand those as opposed to just kind of casually being able just to work the problems. So in Unit 2, once we had done those things, we then had a session where we came back and said, well, we understand about decimal points now. Let's see if we can encode fractional numbers using one of the standards. And the standard we chose to use was the IEEE 754 floating point standard, single precision. It's important we say single precision there so we know that it's maintained in 32 bits. It would be, more bits if we were doing double precision, for example. And then we talked, we probably haven't talked in this class yet about transistors. We'll do that tonight. And we may briefly go over transistor circuits. I think we took the diodes and we did a diode circuit session here. So tonight we're going to be attacking Unit 4. And the units, by the way, don't necessarily map to nights. They may be across multiple nights, or I may do 2 units in a single night. But they kind of group together work which needs to be put together. First part of tonight, we're going to talk about combinational logic and the underlying Boolean algebra that supports it. Now, newsflash, to any of you that are taking discrete math, we'll cover some ground that discrete math also covers. We'll do it slightly differently with a different emphasis. And you need to remember when you're in this class, do it the way I said, and when you're in their class, do it the way they said. But we're doing it for different purposes. Ultimately, things like truth tables and even some of the Boolean algebra identities and duals and things like that are properly taught in discrete math. And you should be bringing those skills with you so that it's review here, but I find that that's not necessarily true. So we will cover the necessary parts of that. Combinational logic, of course, is very important because it is what we would think of as real-time logic. When some inputs change, the output immediately changes in synchronization with them. So if we define a function, which is a function of those inputs, the output is assumed to take no time to change and is a result of combining the inputs through some sort of internal function. In real life, that doesn't quite work that way, but we'll wait until we're in sequential logic to take a look at that. Part of the problem is that it takes a little bit of time after the inputs have been manipulated for that signal to make its way all the way to an output. Even if we're talking about small circuit boards or small chips, there is a finite amount of time that electrons can move. And because of that, combinational logic is kind of an exemplar type of this is the way we know it looks like it's working, but to make it do that, we also have to do some things in our design. And we'll understand that pretty well in a couple weeks. Boolean algebra is the idea that we're going to take, using binary arithmetic, and map some rules on top of that where we can talk about the behavior of those binary bits and binary digits under certain given circumstances. And there's a set of rules that we'll talk about and some laws and some principles that dictate how Boolean algebra should work. Then we're going to talk about transistors. In particular, we're going to talk about what are called BJT transistors, bipolar junction transistors. And in particular, we're going to be talking about NPN transistors, and we're going to use them as though they're switches as opposed to amplifiers. But we'll need to be able to detect if we do a design whether or not we've accidentally put them into an amplifier mode, because that would prevent them from operating correctly as a switch. And since one of the things we'll see when we talk about transistors is they're really a good way to take something that is a small signal and be able to control things in the world, where the world might not be able to be readily controlled by small signals, but may need bigger signals in order to make things operate correctly. And then in the next class, of course, we'll talk about some optimizations and things we can do with the stuff we're going to learn tonight. So I thought we should just take a quick eyeball at that. Does anybody have any questions about any of the material we've covered thus far? Because it may seem like you're in a different class all of a sudden tonight, because we're going to be on a totally different subject. Okay, I shall assume your silence means that you are able to do everything up till now, and that I don't need to review any of that tonight. So let us move ahead. Have to keep an eye on the time tonight because we have a lot of material to cover. So let's start a little bit of talking about, I'm going to blend Boolean algebra and combinational logic together. I'm going to start out by introducing the idea of something called a truth table. Now, like I say, in discrete math, you've probably already been introduced to these. However, I may do them a little bit differently, and so do them the way that I'm doing them when you're dealing with me. First of all, I'm going to make a table. I'm going to label the inputs, maybe A, B, C, D, maybe just A and B, maybe just A, maybe A, B, C, maybe, I've got a whole bunch of inputs. Well, I'm going to start with a 2-input truth table, and I'm going to yield one output. Now, here's the notion of how these tables are looked at. In the columns labeled A and B, we consider those to be the inputs of a particular Boolean algebra function. And depending on how those inputs are arranged, we'll produce an output, which we label Y in this case, that will be invariant given those 2 inputs. So it's not like sometimes A and B do this and it causes Y to do this. Sometimes they do. No, rather there's going to be an equation which describes this truth table and is actually descriptive of the way the table actually works. Now, we could label our inputs and outputs, and sometimes will label them with things like true and false, or with things like high and low, or even things like 5 volts and 0 volts. But we're going to stick to binary numbers for now. And we're going to produce the numbers in our table in normal binary counting sequence. So I would put them in this order naturally. Now, you should be able to see that there are no other possible combinations of 2 inputs. And that leads us to potential formula. And the formula says that the number of lines in the table is equal to 2 raised to the number of inputs. So we would expect if I had 4 inputs that there would be 2 to the 4th 16 lines in the table. And that is true. So one of the things we can determine is the number of lines in our truth table is going to be dictated based on the number of inputs. Now we will have a separate truth table for every output. If this same table produced a second output, we would write a second table, or we might collapse maybe we're going to call it X or W. Let's use W. And we'd have 2 separate columns for the outputs. That's getting a little ahead of ourselves because right now we don't have any tables that have 1 output. So let's move there real quick. Let's start very simply, and I'm going to produce a table looks like that. If both the inputs are low, the output is low. If the first one is low and the second one is high, the output is low. First one high, second one low, output is low. If they're both high or both ones, both true, whatever, the output is true. So notice in this case, this particular table is sensitive to when both of them are ones. So if they're both ones, the output becomes a 1. Now, another formula will jump out at us pretty quickly here, which is, since we have 4 rows, how many different arrangements of zeros and ones could we have in those 4 positions? Well, they could go from 0, 0, 0, 0, all the way up to 1, 1, 1, 1. And there exists a truth table which has these inputs and those outputs. Whether it's part of our problem or not, doesn't matter. Those exist. So if we have a 2-input truth table which has 4 lines, that means that the number of possible truth tables in that number of inputs is equal to 2 raised to the number of lines. So in this case right here, that means there are 16 possible 2-input truth tables. Now I'll tell you now, some of them have names, some of them are fairly useful, some of them don't have names, some are less useful, but they do show up. So if I had 3 inputs, A, B, and C, how many lines will be in that table? Put it in the chat. Okay, so the number of lines is equal to 2 raised to the 3rd, which is equal to 8. So there's going to be 8 lines in the table. And if we were to write them out, those are the only 8 lines there can be, or only 3 inputs there can be. How many possible truth tables can I write? Well, there would be 2 raised to the 8th possible tables, which is 256 different ways I could arrange zeros and ones in a Y column here. But once I've done all 256, that's all there are. So you can envision ways that you could conceivably have some pre-worked stuff if you were writing a program that supported truth tables, at least up through the 4. So if we had 4 inputs, that means we'd have 2 to the 4th number of lines, which is 16. And we'd have 2 raised to the 16 possible truth tables, which we know equals 65, 536 possible truth tables in 4 inputs. By then it starts to become, we need to do a little work, and we may see tables we've never seen before, because the 64th K is a pretty big number. Okay, so let's go back. And here's our truth table. This particular truth table has a Boolean expression which describes it. And that particular expression is y is equal to something. Now what we're going to do is we're going to build something called a sum of products equation. And after next week, we'll know how to do a minimum sum of products equation. For now, we don't care. We're just going to let be what be. So what we do is we find all the lines in the table. Let me put it back to that function I originally had. We find all the lines in the table that are true. And they're the only ones we're interested in. And then we write out an equation based on the product of those 2 inputs. Okay, so what that says is y is equal to AB. Product in Boolean algebra is equal to what we consider to be the AND function. Sum is equal to what we consider to be the OR function. When I say sum of products, what I'm talking about is I'm going to have a bunch of things ORed together, another bunch of things ORed together, another bunch of things ORed together. That's all the products. I'm sorry, that's all the summed parts. Each of those things that were summed up are the products. So we describe this looking like multiplication in other algebras. We do this guy looking like addition in other algebras. So since this looks like multiplication, that means we're really doing an AND function. Nothing is added to it or ORed with it. So it's simply a basic sum of products equation where there's only one thing to sum up. And since we have one thing, we don't need any plus signs. This function is a very common function that we use, and it basically has the name of the AND function. I believe I wrote that down, but I'll write it above the table here for the moment. Now let's look at the OR function. It has A, B, and Y, same type of inputs. And what an OR function says is it says if either or both of the inputs are true, the output is true. So this is a 0. All the rest of the lines are 1s. This particular equation says y is equal to A or B. Now it turns out that this is sensitive to zeros. Notice that the only time something peculiar happens, otherwise it's always true, but the only time something peculiar happens is when both of the inputs are 0. And that has some bearing on things. Now let's do our sum of products equation here. We're only going to be concerned with the lines that have 1s at the end of them. So a sum of products equation for this guy looks like y, whoops, that's a p. Y is equal to, first line is not A, B, or A, not B, or A, B. Anytime we have a 0, we need to, because remember this is a product, we need to take and invert the 0 to make it a 1 in order to get the 1 of a product which was two 1s. So in order to describe that, we need to say it's whatever not A is plus A, or multiplied times A, or AND with A. The next one is A not B. And the last one, of course, is AB. Had the first one been in there, it would have been not A, not B, because that's the only way we would have gotten a 1 out if that had been a 1. Now you'll notice these two equations are both sums of products. The top one is called a minimum sum, not sub. And this guy is just called a sum of product. An S on those. Now you might say, well, how the heck did we get from here and here, and they mean the same thing? Well, I'll teach you some reduction techniques that allow you to algebraically take this and turn it into that. And we need a little more information for it. It would make sense to everybody in the class, so I'm going to stay away from telling you much about it yet. But we have two functions now that we know the definition of. First of all, if both of our inputs are true, the output is true. That's an AND. An OR says if either of the inputs or both are true, the output is true, which is just another way of saying if both the inputs are false, the output is false. Now, one of the reasons we don't say that a lot is because there is a thing called positive logic and something called negative logic. Now, we do most of our work in positive logic. There are a couple of times when we have to dip our toe into negative logic, and I will warn everybody in the class that's sensitive to plug their ears while we talk about it. And we go in there and we come right back out again, having converted something into positive logic into something that's cool. But in general, we want to work in positive logic, and negative logic is saved for special purposes. If we mix them, we will become confused. So we want to remember that we're working in positive logic. In positive logic, what it means is 1 means true, and in negative logic, it would mean 0 means true. And that can confuse people really quickly. So I will warn you if I start to dip into it. And the first time I start to dip into it when we talk about something called Demorgan's theorem. And we may do that tonight for a bit, but you want to steer away from it. Okay, everybody give me a little green light there to say you're still there. Remember, take good notes. Don't rely on a recording or somebody else's notes. You take good notes, because that's the best way to absorb this stuff. And I've proven it time and time again with people. And I've always had the one that say, oh no, I'll record the session and then I'll just play it back and watch it. I'll know everything then. Doesn't seem to work that way. Okay, now, obviously we could take any particular Boolean equation. Let's do one here. And I'm just going to give it an arbitrary set of outputs. Okay, the truth table I wrote right now has a name. It's actually called the XOR function, XOR. And in general, because it uses a different symbol that's not a multiplication symbol or plus symbol, we would not express it except when it's in a very high level macro type of way of describing what something's doing. And we'll see a couple times when we use it outright just to mean that. But in general, we also need to know if we did a sum of product, could we write it out and would it do the same function? And the answer, of course, is yes. Now, all of the lines that end in 1 have a name. They're called fundamental products. They're sometimes also called min-terms. So expect both of those names to be talked about. It's either a fundamental product or a min-term. By fundamental, we mean that it's required in the sum of products equation. Now, you may do some stuff, and it may seem to you that a problem that looks like this is an answer that you would want to give me for some reason. Now, you would not. The reason is this is not a sum of products equation. This is what's called a product of sums. Notice we do the sum first, and then we take the product of those. This is no. Whoops, that's not no. Don't turn something in that way. We want everything to be a sum of products, which are things that look like this, where we do the products first, and then we sum them up, which is basically to say the ands happen before the ors. You'll notice here also I'm using an exclamation point to indicate negate this variable. It's not A. When I write this out, or if I have a better font, I'll actually put an overbar over the A. I won't put an exclamation always in front of it. It'll have a line over the top, and that means not as well. So you'll see both notations. So if I were to ask you here, what are the min terms of this particular equation? You would tell me the first min term is not AB, and the second min term is A not B. If I ask you what the fundamental products were, you'd give me exactly the same answer. So let's write out the sum of products equation. We don't care if it's a minimum right now. We're just going to write it out. Y is equal to not AB or A not B. Notice it's very similar to the first part of the regular OR. The only difference is the OR also says if both of them are a 1, we want to capture them. Now this has a kind of higher abstraction thought about it, which if you thought of it this way, this produces 1s when the inputs are different. Produces false when the inputs are the same. So you can imagine this being used in some sort of a comparison circuit where we're trying to identify whether something is different or identical. And of course, we would expect that there is a function looking like this. This has a name also. This is called a snore. Like you're snoring? Snore. Try saying that. That feels really good. Nobody's listening. Just say it out loud and see if anybody looks at you funny. That's a snore function. And it uses the same sort of symbol. I'll show you the difference when we're dealing with it. But the idea here is this produces a true when things are equal. So you can imagine this definitely would be coming in handy if I were checking 2 binary bits to see if they were equal. When they're different, I get a 0, so I could deal with that false and do something about it. So those are some 2 input ones that we would immediately fall into if we were working with Boolean algebra a lot. What about is there a 1 input one? Can I just have an input? Well, let's see how many lines should be in this truth table? Well, lines were 2 raised to the number of inputs. Okay, so it'll be 2 raised to the first, or 2 lines will be in this truth table. Okay, so the first line is going to be a 0. Second line is going to be a 1. Well, it seems like we'd run out of things to do there really quickly. How many possible truth tables can we write? Well, that's 2 raised to the number of rows. The 2 raised to the 2 is equal to 4. So there's 4 possible truth tables. We can write them all out. The first one is this. The second one is this. The third one is this. And the fourth one is this. So let's see what these equations are. Again, the columns would be labeled A. This column, first column is A, all the way down here. Could be S, but we'll call it A for now just to be consistent. And the outputs higher letter. So the first truth table here says y is equal to 0. That's the sum of products. Since there are no fundamental products, we can't write a proper, but we accept this to be one of the proper sum of products. The next equation, y is equal to a. Next equation, y is equal to not a. And finally, y is equal to, as a fundamental product, it's going to be not a or a, which by observation we can see reduces to y is equal to 1. But this is the reduce, so this, we don't know how to do that yet. We just know this would be using fundamental products. That's the fundamental products that make up the sum of products to represent this equation. This particular function is used a lot where the output is identical with the input. Its formal name is a buffer. This particular function has the name of being an inverter. It inverts the input. Whatever the input is coming in, the same thing happens going out. Now there's kind of a funky little thing going on here as well, that it's perfectly legit for the moment, although not sum of products, to think of this in that form. And these actually mean something different. This says take A and invert it. This says take A and when you produce the output, invert it. We'll see why that matters later, but just sometimes you'll see when the not sign is applied doesn't really matter. Parentheses will cause different things to happen. This is clearly not sum of products, but we may see that there's times when that turns out to be useful. Okay, let's take another equation here. I'm going to do this one in 2 variables again. Okay. This table, if we take out the fundamental products, says y is equal to a ANDed with not b, or a b. Now later on, we'll be able to reduce that. What we'll see, and we can do it by observation right now, we can just see y is equal to a and b doesn't matter, right? I think I told you all this. This is deciding, whether or not we're going out tonight, me and my wife, right? My wife is A, I'm B. She says we're not going, we're not going. Doesn't matter what I say. Same thing, she says we're going, we're going. Doesn't matter what I say. So sometimes one of the inputs supersedes the other, and in this case, if we were building a circuit, none of that would have to be built because we'd be able to reduce the equation in advance to show that that wasn't a necessary component of the problem. Everybody reasonably good? Give me a green light if you're reasonably good with what we're talking about. Okay, those are reasonably green. Okay, let's take a 3 input. If you notice, I'm doing these in binary. The thing you can observe, and we'll come back to talk about in a different session, is the rightmost row could be written down first by just alternating zeros and ones. The next row over has 2 of everything, but it alternates 0, 0, 1, 1, 0, 0, 1, 1. The next one does 0, 0, 0, 0, 1, 1, 1, 1. If this had 16 lines, what do you want to bet that the first 8 are zeros and the last 8 are ones? They are. So by using binary numbering and keeping them in sequence like this, we can, by observation, check to see if we missed something. But additionally, it's really easy for us to count. This is equal to 0 in binary, 1, a 2, a 3, a 4, a 5, a 6, and a 7. So, and we know since there's 3 bits here, there's going to be 2 to the third number of numbers. So that's up to 7 if we include 0 as a number. So let's put and build a little truth table here. For whatever reason, oh, 9, that was fancy. For whatever reason, this is the truth table that we have. Now, we don't know whether or not this can be reduced. All we want to do is write down the full sum of products equation. Why don't you take a shot at that and then cut and paste it into chat? And don't worry about reducing it. We'll do that in a later episode. Okay, looks like some of you are coming up with answers. Let's do this together now. We want to take the rows that have 1s in them and simply extract the input fields that are there. So if I'm on the right keys here, y is equal to, actually, yeah, let me make them separate. Y is equal to, first one is not A, not B, C, or not A, B, not C, or not A, B, C, or A, B, C. Now, if we had these as signals and we hooked them up so that they produced either 5 volts or ground as a plus signal or a negative or a ground signal, meaning zeros or ones or trues or falses, arranging them this way means that anytime I change these 3 inputs, this table will be rendered. This is what's going to happen. And so, we're just a step away from being able to say, well, we could actually build one of those if we knew how to build those gates. And we call a particular function a gate. So for example, when I write down y is equal to AB, I'm going to later call that an AND gate. I write y is equal to A or B. Oops. I'm going to call that an OR gate. And you'll see why later, because they apply to components in electrical work that are called gates. Because they're basically gate of the logic. The logic input gets gated so that it either goes through or it doesn't based on the equation you've given it or the way the chip was built. Okay, so we're pretty good at this now. I mean, we didn't have much problem with that. And while it may seem difficult on the surface and can be made to be very difficult, we don't want to do that. But we now have some things. Now, we may not know what to do with those yet, but that's okay. I'd rather you be able to take a table and give me the outputs from it than to not. So let's talk about some of the rules of Boolean algebra. Do you remember way back in elementary school somewhere, probably, maybe 7th grade, the arithmetic teacher told you about the commutative law, the distributive law, and the associative law. And you kind of filed it away and you knew that it was there and it was just some big words. Well, we kind of know about those, right? In commutative, we know that if I have a number and I add it up, I'm going to be able to make that equivalent. I'm going to write like a bunch of zeros to mean equivalent to, not necessarily identical to. So the order doesn't matter in the commutative law. I can do one before the other and that's fine. And again, this 14 itself doesn't have to be the number 14. It has to be something that could produce a number, added to something that could produce a number. As long as I'm using the addition, I'm talking non-Boolean algebra here. As long as I'm using addition, it doesn't matter which order I do those in. The same thing was true if I added parentheses. Oops. Let me put them in the same order here. And I stuck some parentheses on these such that I grouped those together and then added the 25. Or I took the 14 and I added it to something that I had pre-added here. And for certain operators, we demonstrated that how we associate them doesn't matter. Again, we could do the 14 and the 25 first. Now, this is not true if I change the operator, right? This works for plus, this works for multiplication, but this doesn't work for minus or division, perhaps other operators like the modulus operator. So as long as we know what the operator is and that it's commutative or not commutative and that it's associative and not associative, then we're in good shape. We also had a distributive law. You know, it was something, I don't know, we said A, B, C, something like that. We could write that. It was equivalent to AB plus AC. Notice here I use variables rather than using numbers, but as long as it's something that could produce something which could be multiplied times something that had been added up in that particular algebra, we could do this distribution of terms. Everybody remember that? Give me a little green light if you kind of remember commutative, associative, and distributive laws. And you thought you'd never have to see them again, didn't you? Yeah. I was kind of unhappy when I saw them. But, I mean, once you know which operators are able to do that, that makes coding often, particularly if you're in software coding, very interesting. For example, if foo is a function and goo as a function, do something. Well, this function returns a Boolean operator. Let me just mock one out here. Pretend like it returns a bool. Don't know what language we're in there, doesn't matter. Then there it's going to return either a true or false, and goo does the same. We don't even care how it got its answer. But programming languages have something called short circuiting in the things like ands and ors. Here's the deal with an and. You remember the and truth table looked like this? The only time we got a 1 when both of them were a 1. Well, in most programming languages, unlike in hardware, if we demonstrate that this is false, we don't have to do that at all. And as a matter of fact, we don't do that. That's confused many a programmer when he thought maybe he has a printf in here he's expecting to see, or a sysout, system out type of thing. Well, he's not going to see it if this is false, because false and anything is false. So this can't be true. We'd never go into the loop, so there's no point testing the second one once we've tested the first one. However, if this demonstrates to be true, we need to run GOO, because that's the bottom two lines, in order to see whether or not we need to do or not do the internal part of the if. Same thing happens with an OR. If the first guy is, let's change it to an OR in some programming languages, very often they use vertical bars for that. If this is true, well, that means the whole OR is true. We don't have to do this part. If it's false, we do have to do this piece. But if it's true, we never have to do this. Those are called side effects. And this is one of the places where programmers and hardware people come to fighting with each other, because the programmer swears it's not going to happen and the hardware guy knows it will. We're not going to prevent the second half from being done. The reason it's not done in programming is you could optimize away a lot of code if you can demonstrate the first one. So when you're writing code, one of the simple programming tips is put the thing that's going to be simplest and most likely to be false first in an and put the thing that's simplest and most likely to be true in an OR, so the difficult one may less often have to be executed. So that's just, if you're just thinking about just simple tips for a programmer, that's one I give all my interns, as I give them, that is one of their things out of the gate. Don't over optimize, don't do it too soon. But by the way, there's no reason why, since we know this is going to happen, we can't just write smart code. Big difference between optimizing and certainly big difference between being clever. Nothing clever there is going on. It's just good programming. Okay, so let's move ahead here now. One of the things that we want to do is we want to look at some things like those laws. If I have a binary thing and I OR it with something else, it in fact can be reversed. So OR is commutative. If I have something that produces a Boolean result, it is indeed associative. If I have something which can be distributed across something, indeed it can be. I'm sorry, AC. So in Boolean algebra, just like in regular arithmetic, ands and ors are commutative, associative, and distributive. And we just need to remember that, so that those laws are kind of second nature to us. There's times when grouping helps a lot. And for example, if I'm going to do this, but it looks like doing this is going to produce quicker results, I can rearrange it so that that gets done first. Maybe this is so easy it goes away. And if it goes away, then I might be spending more time working on C. So those are some things that we may happen. Now there's some simple principles. Let's take A and OR it with a 0. What is that equal to? Put it in chat if you know what that's equal to. It's going to be equal to a 0, a 1, or an A. In fact, it is A. Since the second one can never make it true, we only care about what A is. So A is going to be the thing that causes that to be true or false. How about if we took A or a 1? What's that going to be equal to? Put it in chat. Right, that's always going to be true. How if we take A and OR it with itself? What's that going to be equal to? Good, I see some of you have caught on. Put them in chat. That's equal to A, of course. How about A ORed with not A? Well, in this case, if this is true, that has to be false. If this is false, that has to be true. Since one of them or more of them is true, that means this always has to be true. How about that? I'm going to doubly invert A. What am I going to get? Yeah. 2 inversions take me back to what I originally had. So that's fairly straightforward, pretty easy stuff. Now, in algebras in general and in Boolean algebra, it shows rather obviously, there is something which is an interesting concept. And the concept is that once you prove a Boolean expression to be true, the expression itself, there exists another Boolean expression which is also true. It's not equal to the original, but it is true by virtue of the fact you proved the first one true. And so we could go through and do formal proofs of these, and we'd see each one is true. I'm skipping that pain and putting that in your discrete math class. Hopefully they'll do that with you. But here's the idea. We're going to discover something called a dual. The dual is another Boolean equation that is also true just because the first one is true and because we followed some rules to create it. And here are the rules. Anywhere you have an and, change it to an or. Anywhere you have an or, change it to an and. If there's a 0, make it a 1. If there's a 1, make it a 0. Let's go up to our top rule up here. And let's do that. We have 2 things ORed together on opposite sides of an equal sign. So the rule says, replace the or with an and we can do it both places. This is true because that is true and because we used these rules to convert to the dual. So what this says is it doesn't matter which order I and things in, the result is the same. Just like over here it said it didn't matter which order I ORed them in. This is another commutative law. Let's do this guy. Parentheses don't change their position at all. So beta of A, BC is equal to AB, C. And that, in fact, is another associative law. It doesn't matter which order we associate the ands in, they will remain true. Okay, do this one by yourself and put it in chat. Just follow the simple rules, right? Ands become ors become ands, zeros become ones, ones become zeros. Okay, we're starting out with an and, right? Oops. We have an and, which we're going to change to an or. Got some parentheses. I have them on this keyboard anywhere. And then we're going to take the or that's in there and change it to an and. And that's equal to A, B, ANDed with A or C. So this is a true statement. This doesn't look much like distribution, and as a matter of fact, we probably would get rid of the parentheses here, because we've still done what this said to do. So those are the duals of these equations that we proved true earlier, or laws, the associative, the commutative, the associative, and the distributive. This one's not so obvious. Notice here it is in reverse, so this looks like factoring out something, right, almost. But this looks a little more like what you normally think of as factoring. Okay, so that also says that these guys must have duals. So A, and I'm going to put a little X here for an and. See if I can possibly type on this keyboard again. And 0 is equal to whatever A is. A ANDed with 1 is equal to 1. Now, what did I do wrong with these two equations? Somebody get on your mic and tell me.
You didn't change the zeros and ones to its
Excellent.
opposites.
Excellent, excellent. This needs to be a 1. These need to be zeros. So of course, A ANDed with something that's already true is only true when A is true. This can never be true because it has a 0 in it. So it's always false. The next guy here, A ANDed with A would be A, right? It's going to be either both the ones or both zeros. A ANDed with its inverse, not A, is equal to false, because if one's a 1, one's a 0, can never be true again. And then finally, the last one has a dual, but it's identical. The dual is that if you invert A, you get A. So those are all fairly interesting. Now, there are a couple other theorems which I'm going to just present, and then we'll talk about them as we need them. Well, I'll just go with one, a Demorgan's theorem problem here. If I take two things and OR them together, and then after I have ORed them together, I invert the result. That's the same thing as if I had taken both, inverted them first, and then ANDed them together. This is moving into negative logic for a second there, so if you're easily scared, hold your ears for a second. This says we're going to do the function and then invert it on the way out. This says we're going to invert the variables on the way in. If I wrote the truth tables out for these, you'd see they are identical. The name of this function is a NOR function, not OR, meaning that it's going to do an OR and then reverse all of the output. So we have an A and a B and a Y, 0, 0, 0, 1, 1, 0, 1, 1. If we did the OR, we'd have 0, we'd have a 1, we'd have a 1, we'd have a 1. But this says reverse them. So for a NOR, the 1 happens here. All the rest of them are zeros. Now, if you look at this, this says if both of the variables are inverted, give me a true. That's only on this line that could possibly happen, and it's a true. So these two are equivalent. They're part of what's called Demorgan's theorem, which basically says if two things are ORed together and then inverted, that's the same as if the inputs were inverted and then ANDed. But the name of both of these functions, even though this looks like an AND, is NOR. This is called the Demorgan NOR function. This is called the regular NOR function. There must be a dual. The dual says if I take and I AND things together and invert them, I get equivalent to where the name of this function is NAND, N-A-N-D. This says AND two things together and invert their output. This says invert the inputs and then OR them together. And in any event, we could build a table. I'm not going to do it right now. Something you could do on your own or put it on a quiz maybe for you someday. And it basically says these two guys, which we just proved are true because we did them as duals, are true. Now, NOR gates and NAND gates are very powerful. Well, I'm going to show you for much of the rest of the semester how anything in a computer can be built out of some combination of NAND gates. We're going to have all sorts of fancy things we learn. We're going to see other ANDs and ORs and NORs and things. But if I have either NAND gates or NOR gates, you know, Pinky, I can take over the world because this takes advantage of the fact that something that looks like an AND, given the right circumstances, can look like an OR. Demorgan's theorem, maybe I'll spell it wrong. I'll try to write it out here. Demorgan's theorem are these two statements here. So going this way or that way, this way or that way. This is the NAND, this is a NOR, and it's in its name, which basically says do an OR and then invert it. This says do a AND and then invert it. So let's look at how some of these things might be schematically diagrammed. And an AND gate is drawn like this. It's got a round nose and a flat bottom. It has two input lines coming into it and one output line. That's an AND. So this might be A, this might be B, this would be Y. An OR gate has a curved bottom side. The top looks like the other guy. Two inputs, one output. The output's labeled Y. Inputs might be A and B. And this is an OR gate. Now, we had talked earlier about a single input, single output gate. They look like a little triangle. There's some other things that look like triangles too, but this has one wire going in, one wire going out, where one is the input and the other is the output. Now, you might say right now you have no reason to use these, and later on in the semester I'll show you why you might. But more importantly, one of those four things that we said that could be done with a single input looks like this. As A coming in, there's a bubble on the nose of this thing, which means invert, and it has Y coming out. So the function here is Y is equal to not A. I'll put an overbar to indicate not. So a little bubble on the nose of something is going to imply that it gets inverted. I could, and there's times when we might, say we're going to invert it before we go in. Same function, this is still y is equal to not a, but the not actually happened on the a before it went in. This happened on the a on the way out. So these are equivalent. We'll normally use this picture. Now, a more useful gate is this guy. This is a NAND. And we'll literally build everything we can possibly build out of 2-input NAND gates. And most of computer science, including sequential logic, can be built using them. This is A coming in, B coming in, Y going out, but Y is equal to A and B ANDed and inverted. Notice that this thing right here has two terms inverted. So this isn't exactly a sum of products. So we're going to watch for that later. The other way we can draw a NAND gate, called the Demorgan NAND gate, is to draw an OR gate, but invert the inputs. Both of these are NANDs because of Demorgan, even though this one looks like an OR gate. Looks like an OR, right? This looks like an AND. So this guy right here is basically ANDing and then inverting. This guy is inverting and then ORing, but these are equivalent. So we'd expect the NOR gate to look like this. Bubble on the nose. OR first, invert out. Or it might look like an AND gate with the inputs inverted. So these are called NOR gates. The bottom one is the Demorgan NOR. How do we use these? Well, let's say somebody gave us a really simple equation and said we could use any of these. The equation is y is equal to AB or CD, sum of products equation. We see we have two things, in each case ANDed together, the result ORed together. So we could envision writing two AND gates, one OR gate, taking these as inputs to the OR gate, taking our final Y right there, and then our inputs coming in would be A, B, C, and D. So if we had a circuit which could do the AND function, and we had a circuit, this is a terrible looking OR, but if we had an OR function, the result here would match the truth table for whichever truth table this happens to be the equation for. 4 inputs, so it's one of 64K or 65,536 different possible functions. But we can tell here that in that table, there are only 2 min terms available. We know the first term here is everywhere A and B are 1. We know the second term is in the truth table everywhere C and D are 1. So that stands for multiple lines. This is a reduced equation, which we'll talk a lot about in the next session. Does anybody have any questions about what we've just covered tonight before we change topics? See, this stuff's easy. It's just a bunch of pictures. Okay. Okay, let me find my clear button here. That's not it. Okay, now, like I say, some of you will have had this in discrete math, and it's very similar to what we're doing here. Be very careful with the nuance. I don't want the answer you're going to be giving me from what they told you there. I want what I tune it to here, particularly once we start reducing the equations into forms that can be built with hardware. So be very careful about, well, I'll just grab, chapter 10 or whatever it is from your discrete math book and read that instead. Make sure you keep good notes on what Bastien is saying. It's important. Common mistake. I've had too many people, and usually what happens is they have discrete math at the same time, same semester. So just beware. Okay, so what we want to talk about next is transistors. But before we do that, let me minimize that window for a second and go grab this. Okay, everybody remember this guy from last time. Might as well. So let's work out a problem here quickly so we can understand the pieces that we need to know. In this particular picture, we have current flowing this direction. We know because the arrow, this thing here, this piece right here, points in this direction that the LED is in the circuit correctly. We also know the current flows from the high part to the low part of the circuit. So it would make sense around the loop that that's the direction current is flowing. We also should be able to compute that particular current, and in this case, given very little extra data. The data we need to be given is going to have to be minimally some piece of information about what the voltage drop is across the resistor or what the voltage of the battery is. We've been told to deduce something here if we've not been given any other info. So let's assume that we've been given that this particular battery is producing 10 volts. And what we've been asked to do is we've been asked to determine what the current is through the circuit, or we've been asked to determine what the value of the resistor is. And we might ask, what is the color code of the resistor? That might be how we ID the thing. So first of all, we examine this to find out, is this an LED or a regular diode? If it's a regular diode and you've not been told differently, you're going to use a 0.7 volt drop across a regular diode. That's VF. If we're going across the LED, VF for this class is 2.1 volts. Unless you're told otherwise, and you might be. This is a nominal value for just an average LED, but I happen to know for particular ones different limits and things on them. The other thing we were given is a current when it's an LED to use in the circuit. Now, if we were using a diode, we would have to either deduce that or we'd have to find out what that is some other way. But for an LED, we've been told that we have between 15 milliamps up to 25 milliamps as desirable values. 15 being when it's bright enough to see, 25 being when it's ready to be burned up. It's actually a little safety factor in here if we had real LEDs, but we're going to make it safer by picking a good range and then to us a number working here with 20 milliamps. So we know what I is here. We know the voltage drop across the LED because we've not been told anything else, and that's going to be 2.1 volts. we need, in order to do the resistor value, we need the voltage that's right there. So we know if this starts at 0 volts down here relative to ground, and this is a drop of 2.1 from some higher voltage over here, the voltage here has to be 2.1 volts. Now we're going to be back up to 10 volts relative to ground by the time we get here. So that looks like we need to take 10 volts minus 2.1. So let's pop this guy up here. Was there a stay on top? I think that's what that guy is. So we can take 10, and we can subtract 2.1. We get 7.9 volts. Okay, now remember, I'm doing this without notes or anything here, so I'm doing the math the same time you're doing it. So I'm subject to making typos or math errors. If I do, you know, we'll fix them as we go, or if they're just making a point, I'll leave them alone and let you resolve them when you go through your notes. But what we have now is we have 7.9 volts. We have a current which is going through the resistor. What's missing is the value of the resistor. We know Ohm's law says V is equal to IR. So if V is equal to IR, we can take and divide the voltage by the current to get the resistance. So 7.9 divided by 0.02, which is 20 milliamps, is equal to 395 ohms. Now we're given a clue here that we're not going to be able to buy this resistor because it has more than 2 digits in it, more than 2 significant digits. So what we're going to need to do is we're going to need to find out what value is close to 395. So you may have these memorized or you may not at this point. We need what values are available. So standard resistor value here, 395. Well, looks like we could get either a 10% or a 5% at 390. That's pretty close. So let's go for a 10% at 390. So we know the real resistor we're going to get is 390 ohms. And we said we're going to make it be 10%. So it's possible that we take 390 and we add 39 to it. That's 10%. We get 429. It's possible that it would have that large of a value. Larger value of resistance, less amount of current. So you would check this value to see whether or not it's going to be bright enough to be turned on. We also could take 390 and subtract away 39. We get 351. Less resistance, more current. So this is the guy that potentially we want to check for its power rating. And also we want to make sure we haven't increased the current above 25 milliamps. So let's check those two. We'll clear out the value, take 7.9 and divide it by 429. Let's see what in the world I just did there. So it's 18 milliamps. $18 is between 15 and 25, so check, that's safe. Let's try 7.9 divided by 351. That's 23 milliamps. That's still safe. Now to get the power, we need to take this current times the voltage, which is 7.9. And that's going to give us 178, or roughly 180 milliwatts. Our choices of value are 125 milliwatts, 250 milliwatts, and 500 milliwatt resistors. All these are milliwatt. That number is too big to use 1/8 of a watt. So we need these to be quarter watt. Okay, so we're going to use a 390, 10%, 1/4 watt resistor. Everything checks out as being safe. So we need to find out what the color code is of a 390 ohm 10% resistor. So let's look that up if we don't have it memorized. Okay, 390 is going to be orange, white, 10 is brown. Where's my page? So the resistor we're getting here is orange, white, brown. And we said it's 10%, so that's silver. So we go to the store, we check it, it has the right color code on it. How do we know that we got a quarter watt resistor, one that's 250 milliwatts? Somebody get on your mic and tell me. Nobody want to give me a shot at that? We know it's 390 because it's orange, white, brown. We know it's 10% because it's silver. How do we know that it's a quarter watt? Well, if it's loose, we don't know. If it's in a package, the package will tell us. They're not marked in any way. Give me a green light if you remember me saying that last time. Obviously, if you didn't, give me a red light. Otherwise, I won't know you're participating. So that should have been in your notes. And that's one of those things that's, you know, when you review your notes, if you're just making a pile of notes hoping on the test day to pull them out and rewrite them or to use them then, you're going to be so far behind. You've got to do this as you go along and remember these things. These are important. It's not just you're going to be able to look them up every time. Okay, so you could work one of these, right? If I were to give you a problem like this, no problems, right? I mean, it's straightforward stuff. I just very routinely went through each piece, solved some algebra, and wrote down the numbers that I needed. Okay, so what I want to introduce you to now is a different circuit element called a transistor. And then we'll do a little circuit problem with it. Let me, well, probably the best way to do that is to leave this open, but blank. Okay, so here's what a transistor does. I'm going to give you the 50-cent description of how they work. Okay, a transistor of the type we're going to be using is basically made up of two differently doped pieces of silicon. So we're going to be working with a silicon transistor. One part is doped. That means mixed with another chemical that has extra electrons, or mixed with an extra chemical that has too few electrons. One's doped with too many electrons for silicon electrons, and the other part too few. So we have what's called P material, we have N material. Now I'm not going to go through the physics, don't need to. You can still understand these without understanding all of it. Those of you that are interested, by all means, make it your goal to learn that, but it's not essential to our discussion that you understand all the nuance. I'm going to cut some corners, but I'm not going to really tell you anything that's wrong. I may wait till I tell you all of the facts about something, but I'm not going to literally just tell you this is the way it is because it's broken, type of thing. But P material and N material are really silicon that has too much electrons or too few. They're butted against each other in something called a PN junction, just like a diode was. So it's like a pair of diodes. If I had a diode which had negative and positive put together, or I could have one put positive and negative together, what would I have if I shared the center piece? I have a piece of negative bumped up against a piece of positive, bumped up against a piece of negative. I have one diode here. I have another diode here. Well, although I can't do it with diodes, I have to make very sure that this P material is very, very thin. And I also have to make sure that one of the pieces of N material is doped a little heavier than the other. I basically built what's called a transistor. The type we're building is something called a bipolar transistor, the bipolar junction transistor, which is abbreviated BJT. It comes in two forms, NPN or PNP. We're going to almost exclusively work with the NPN form, not because it has any particular goodnesses over the other, it's just in the types of circuits we would be building, it's more appropriate. And that you can't understand yet, but later in the semester, if we have time, I'll explain that statement to you. NPN simply means that I have two diodes bumped against each other, two junctions. And my transistor, because of that, if I hook a lead to each of the junctions, has three terminals. One is called the collector, another is called the emitter, and the third is called the base. There is a PN junction between the base emitter. There is a PN junction between the base and collector. So that must imply, if we're using NPN transistors, that the base is P material and the other two are N material. Now, a bipolar transistor is designed to be a current amplifier. It doesn't amplify voltage, although we may often use it to give us the effect that it was. Rather, it amplifies current. Now, the current it specifically amplifies, okay, so it amplifies the current going into the base, coming out the emitter, and the amplified current is seen going into the collector and out the emitter. Okay, so what that means? Give me a little picture, please. Well, okay. I'm going to draw a circle. Oops, not with that tool, I'm not. I'm going to draw a circle, and I'm going to draw inside it a straight line, and then two diagonal lines, and another straight line. These are the three terminals of the transistor. A transistor's name is usually written with the letter Q because T was taken up with transformer, but Q is used as the name. So Q1 would be the first transistor in a design. In the circuit, This is the base of the transistor. This is on an NPN transistor. It is the P material. This is the collector. This is the emitter. Now there's one other notation which on a PNP transistor or NPN transistor is going to be opposite. On the transistor we're using, NPN, there's an arrow pointing out the emitter. That means that current is ultimately coming out the emitter. So current will ultimately go that way out of the transistor. Now a transistor can be biased in the same way a diode can be. The only thing is it has two different places to be biased. One of the bias points is across the base emitter. The other is across the base collector. Now, if we're amplifying, so if we're acting like an amplifier, the base emitter will be forward biased, but the base collector will be reverse biased. So this is base emitter. This is base collector. This will be forward. This will be reverse. If we're working like an amplifier. And how that works is some amount of current, I'm going to call it IB, goes into the base. The transistor, through its internal properties, which we're not going to say how it does it, takes and multiplies this current times a number called beta. I write the Greek letter beta. It's equal to some value. Let's say it's equal to 100. And then it takes and produces a current which comes in the collector and goes out the emitter, which is basically 100 times, or beta times, IB. Oops, that's a B. Little current in here, big current passes through the transistor. So you can think of it as though it's a gate that we're opening up a little or a lot, and the current here is following with this multiple number of times. Now, if for any reason this becomes reverse biased, doesn't matter what this is really, the transistor becomes cut off, meaning it will no longer amplify. So zero current will be coming out the emitter in that case, and zero current will be going in the collector. And of course, zero would be going across the base emitter because we had reverse biased it, meaning it can't go through here. So there's one other state we need to worry about. What happens if both of them become forward biased? Well, if they do, we reach a condition called saturation. Saturation is where we want to operate when we're turned on. Basically, what it says is that when we take the base current coming in and beta and multiply them together, the value we get is bigger than the current we're allowing to flow through the collector emitter because of a resistor we'll call RC, or the collector's resistor. This will limit it. Because of that, it's saturated or fully turned on. So if we operate between cut off and saturated, we operate like a switch instead of an amplifier. And in most computer applications, if we're digital, we want to operate like a switch. So we'll want to ensure that either we're cut off, meaning we're reverse biased, or we're forward biased so low that we can't turn on the diode, and we're saturated, meaning that the value is turned on sufficiently to turn on, for example, an LED. Purpose for doing this might be We have an LED we want to control over here, and the amount of current, 15 or 25 milliamps, is too much for whatever sits over here driving the base. Okay, I want to bring that into the form of a circuit so we can start talking about it a little bit. Wait a minute here, I can't find it. Oh, I know what I need. I need that. Okay, here's a circuit using a transistor. And believe it or not, we're smart enough to actually work this already. But we need to go through an example. Notice I took the circle off that would normally be drawn around this because sometimes in the symbolic symbols for the thing, the circle is missing. It's not necessary. But it's labeled Q1. Notice in this circuit, I have two batteries. One that controls the collector side, VCC, and we have one that controls the base side called VBB. We have a resistor over here to control the current through what's effectively a diode, the base emitter junction of that particular transistor. And we have a resistor up here which will limit the amount of current that can flow through the LED. Notice the LED is in upside down compared to the last picture because current's flowing up and through the transistor that direction. It has its own battery this time. Reason for controlling it this way is if we pretend like VBB is really the pin on a circuit board somewhere and it can either supply nothing or one, nothing or 5 volts, then this little amount of current it can supply could turn a transistor on, but wouldn't be sufficient to turn on an LED. So there's some pieces here we need to do in terms of learning about how we would configure this circuit. First of all, let's identify some currents. There will be a current which flows through the LED, through the resistor, and then through the transistor, entering on the collector. Collector's on top. This will be called IC. It's the collector current. There will be another current which flows through the base resistor, through the base emitter. This is the base on the transistor. This is the emitter on the transistor. It will be called IB. Important fact. In order for this to operate like a switch, this battery has to be either 0 or less than 0.7 volts, because 0.7 volts is what's required across VBE. It's a diode, right? If it's turned on, allowing current to flow. So as long as this battery is less than 0.7 volts, this transistor will be turned off. If, however, this transistor is turned on higher than 0.7 volts, and then as long as there's something that can drop, if it's exactly 0.7, there'd be nothing left to drop across this resistor. So if this was, let's say, 0.8 volts or higher, then we've got enough to have a voltage drop. We would have current flowing. Our goal is to act like a switch. This is on or this is off. So if this is less than 0.7 volts, this should be off. If this is higher than 0.8 volts, then some current will be dropping across VB, but the base emitter will be a diode operating with 0.7 volts dropping across it. Now, the current that comes out of the emitter is called IE, cleverly. It's equal to IB plus IC. When it gets to the bottom down here, it will split again, and IB will continue back to the battery. And on this side, IC will continue back to the battery. Now the transistor, we want to operate as a switch. That means that this current times beta must be larger than this current. If it was exactly the same, we'd be operating like an amplifier. We want it to be larger, so this current cannot reach that value, limited by this resistor, of course, so that we're literally switching it full on or full off. We need to have beta. If I don't give you a value for beta, assume the number 100. Write that down. That's on the test. Now, some other facts. If the transistor is turned on, the voltage drop across the base emitter junction is going to be 0.7 volts. If it's turned off, then we're going to see no drop across this. And depending on what the battery is, we may see that voltage at the top of it. But normally, if we just remove the battery, the two aren't even really effectively in the same circuit. So we would see 0 volt difference between the top and the bottom, which is too low for current to flow. Now, if we're in saturation, which is IB times beta is greater than this, then the voltage across the transistor from VCE in saturation has to be such that VBC is forward biased, meaning that C has to become higher than B. And for that to occur, we would, I'm sorry, I said that wrong. We would have to have this go into saturation. This would have to make itself have a value which approached this same 0.7 drop we had on this side. If we did that, let's say we reached exactly 0.7 lower, then C and E would be equal to 0 volts. So VCE, for design purposes, we can assume it to be 0 volts across the transistor if the transistor is fully on. So fully on and saturated. If it's not fully on, no current is flowing, or we're in the amplification range. If we're in the amplification range, we could compute what beta is, and we'd see that we don't want to be there. If no current is flowing because this is reverse biased in both directions, then the voltage we see here will be equivalent to the top of the battery because nothing can drop across the resistor. Now, in real life, this is probably closer to 0.3 volts, the difference between C and E. So chances are pretty good on a test or something, I would give you a different number other than 0 volts. If, however, I gave you a number which was higher than 0.7, so if it's greater than 0.7, you are not in saturation. You're working like an amplifier. And because you're an amplifier, you could figure out what beta was, which you can't figure out if you're in saturation because we've saturated thing beyond that number. We know beta is much bigger than the value we used, so we can't tell you what it is. So saturation, I can't tell you what beta is. If I'm not in saturation, I can compute it exactly. If I'm cut off, it has no effect because there's no current flowing anyway. So now, in our circuit, we have some things that we need to know about the transistor. One is what beta is. We'll assume 100 if not told otherwise. If the transistor appears to be on and saturated, we know we've got a 0.7 volt drop here. If it's saturated and I didn't tell you otherwise, we have a 0 volt drop here. Those are all things to know. And I would commit those to memory because they're simple. What else do we know? Well, we know what IC is. In this circuit is lighting up an LED, so it's going to be between 15 milliamps and 25 milliamps. And we'd be wise to use 20 milliamps as our design value. We also know what the drop across an LED is. If I don't tell you otherwise, what's that? 2.1 volts. Now, clearly, you don't know enough to solve the problem yet because we don't know what VCC is and we don't know what VBB is. I could give you something like the resistance across, or I could give you the voltage across RC or resistance or something, and you could figure out what the battery is. That would be a problem. But for beginning problems, I probably would give you this value and to give you that value. Okay, anybody have any questions at this point before we go on to solving one? Give me a green light that shows me that you're listening. Okay. Okay, good. Looks like everybody that's here. We got one. We're still missing one person. I hope that they're not hoping to get notes from you later and figure all this out. But what the heck. Let's do a problem now, and we'll see how much of that you actually have taken in. Because this is the sort of thing that if you work a couple and you take in what's going on, you'll really understand how transistors work without having to go through. I'm going to teach you, 6 weeks of physics, and by the time you're done, you've forgotten why you're even bothering. You're going to have a practical reason. Literally, if we were in class, next class, we would build this circuit, and you'd go pick out of a box the correct resistor. Okay, let me re-grab this picture because I can't erase it easily, but I'll keep it in case I need it for something. Make it a little bit bigger. I can shrink it down. There's no in-between size there, it seems. That's okay. Okay, so what we're going to do is I'm going to tell you that you have some standard parts, meaning you got a standard transistor, you have a standard LED. We're going to use the minimum wattage resistor we can use that is safe to use, and we're going to use the value that's closest to the computed value, meaning that if it only appears as a 5% and it's closer than it would be as 10, we've been driven to 5% resistors. Now, although we can't see the ground symbol down there, we're going to say that VBB is 4 volts and we'll say that VCC over here is going to be 15 volts. Now your mission is to, when this battery is producing 4 volts, have this LED turned on. And when this battery is replaced with a value of 0 volts, make sure it's off. Let's think about that condition for just a second. Let me switch colors here. If this is 0 volts, how much current is flowing through this circuit? Well, none, because the top of the battery and the bottom are both 0. So since nothing is flowing through here, this cannot be 0.7 volts. That means the transistor is not turned on, meaning no current can flow there. So if no current can flow there, that means none is flowing through the LED, no matter how much voltage I have. So the LED is off. So at 0 volts, we've built that piece of the circuit. It's off. Now we bring this up to 4 volts, and at 4 volts, we want to make sure the light is on. So why don't you write on the circuit on your copy, of the circuit there, or I guess you could, if you're not able to write on your screen easily with that picture, make a note to yourself of what the numbers we need to know. There's several things we know, and write down the ones you know, and let's see if we can then work this circuit out. Now you should be having fun doing this. If the word fun hasn't gone through your mind recently, put it through your head and think about how much fun you're actually having. If you're going to be really cool and be a computer scientist and make fortune in the future, this is stuff you need to be excited about. And you're capable of actually solving this problem all the way through. You just don't know it yet. And there's one little step I haven't told you, but you could, given a paper clip and, some ice water, you and MacGyver could figure it out. Here, put down the things you think you know. And then there's going to be some things we can compute on top of that. And then there's going to be some things that we don't quite know how to compute yet. Okay, let's annotate our picture here together and see that we are, on track. And if I were you, I'd have this sketched on a piece of paper somewhere where you can write on it. And I would write in pencil if I were you, so you can replace it, if necessary. We know the two battery voltages, okay? They were given to us. We were also told some things to assume if we weren't given further information. Let's start with the LED. We know that the LED has a forward drop across it of 2.1 volts. Let's stick with voltages for a second. We do not know this voltage yet. That's our unknown. We know the voltage drop across the transistor, if we're fully saturated, which is the case we're trying to work on, could be 3.3 volts if the teacher told us so, or if we were measuring one in the real world. But we said for design purposes, we can make it be equal to 0 volts. We also know that if we're in a saturated circuit, the voltage drop across the base emitter is 0.7 volts. So we know a lot about the voltages right now. Let's see if we could actually make it around either of these loops with reasonable values. This is ground. We can't see it, but it's down there. So we know that all three of these points right here are at 0 volts. So by the time we get to here, we're at 15 volts. You put in the chat what voltage we're to by the time we get here. Okay, well, if we were at 15 volts here and we're going to drop right across the LED, 15 minus 2.1. We're at 12.9 volts here. Now, what voltage are we as we pass over the transistor? It would be 0 volts here, right? So the drop across it is going to be 12.9 minus 0, which means this guy has a 12.9 voltage drop across him. I'll never read that again, but I'll try to remember it. Now on this side of the circuit, we're at 0 here. This is a drop across the transistor, so we're going to be higher by 0.7 here. And we're at 4 volts here. So how much is dropping across that resistor? Put that in the chat. Four minus 0.7 would be 3.3 volts. Now, are there any other unknown? Well, you could say, what's the resistance across the base collector? Well, it's 0.7 and 0, so it's a forward bias, just like we wanted it to be. But we don't need that measurement for anything. So I'm not going to dirty up the chart by putting it on there. Now, we need a current. Let me switch colors again. Which is going to flow from the battery through the LED, through the resistor, through the transistor, and back out again. This is IC. And we kind of know what that is because we were told for our LED, we need to keep it between 15 and 25 milliamps. So halfway between that, this guy must need to be 20 milliamps. So we actually know enough to compute this resistor on this side right now. We have 12.9 volts divided by 20 milliamps, which is 645 ohms. Okay, 645 ohms. We'll just leave it at that for the moment. Now, assuming that's the value we had, and we actually could produce the resistor, we know there's going to be a tolerance. It's going to be higher or lower. It's probably not going to be exactly that value. So we'll come back and work on that in a minute. What we need to do is figure out how we're going to compute this. We have the voltage, but we don't have two things. One is the resistance, and the other is the current. We need to compute, see if I can get blue to work over here. We need to compute the base current. And the base current has to be a value that when multiplied by beta, we know beta to be 100, right? That's our, if we weren't told otherwise, that's what beta is equal to. We need, when this guy is multiplied by 100, it's bigger than this guy right here. So here's the rule we're going to use in this class. We're going to take IC, divide it by beta, because beta might not be 100 in a particular problem, and then multiply that times 2. And whatever we get is going to be the value we want our base current to be. Okay, we'll think about that in just a second, but let's do that. So we got 20 milliamps, 0.02 divided by 100 equal that times 2 equals that. Well, we move it 3, that's not quite far enough. We move it 6, so that means this needs to be 400 microamps. So see the big gain we get here? This is very small, and yet we're able to drive a circuit. This could be a motor. This could be something more potent, and we could drive bigger circuits over here with very little current. So our chip, which is supplying, it's not really a battery, it's a pin on a chip that's either 0 or 1, 0 or 5 volts, is able to produce this current or not produce it, turning it on or turning it off. Works kind of like a relay if you've ever worked with mechanical relays. Okay, so we know this is 400 microamps. Now let's kind of check that for a second. If we took 400 microamps, which we have here, and we multiplied it times beta, times 100, we get a number which is 40 milliamps, which we said needed to be bigger than we wanted IC to be. It's bigger by twice. Well, that's why we use this number. We force this number to be twice as big as it might have been for a couple of reasons. One is to guarantee saturation. And the second is that if we make slight adjustments to the actual resistor value, which we know we probably will, we won't find exactly the one, it would have to be an order of magnitude different in order for us to affect this number very much and prevent it from being, when doubled, bigger than that number. So we won't have to do quite as much checking on this side. Another thing we're going to do is if this is a 5% resistor, we're going to make this a 5% and vice versa. If it's 10%, they'll both be 10%. If this is a half watt resistor, we're going to make this one also half watt. We're not going to nickel and dime those things. Sometimes it's cheaper just to buy the same thing rather than to design it, because this is not going to be a high precision circuit. It will work, and you could use this in a pinch to really have something turned on by very little current. But nevertheless, it is not, we're not going to do all of the real world things that we would do if perhaps, figuring out, is beta really 100 or is it 106, which could make a difference if we did this precisely divided by 100. So this multiplied by 2 is a good safety margin down here. Let's figure out the value of the resistor. We take 3.3 and divide it with the 400 microamps. So let me clear this. So 3.3 divided by 0.0004. That is equal to 8,250 K. So 8,250. I'm sorry, 8.25 K or 8.3 K. And that's the number of ohms. So let's take and let's look at what we have available to us. We're trying to find a 645 ohm resistor first. Well, we got something about halfway between these two. Now, the question is, does it matter which one we pick? Well, because they're not right on it, and because we have allowed the safety margin of picking 20 milliamps and things like that, as opposed to 25 or 15, we probably could pick either one of these. Now, for no particular reason, I'm going to pick the one that matches the one in the 10% range. That way, when I go to the store, if they don't have the 5% version, they're probably going to have one of these two. And I'll do my planning as though it's for the 10% standard value. So we'll get a 68 or 680 ohm resistor. So let me write that down for a second. I'm going to write that just on a regular piece of paper for a moment. So 680 ohms. Now the other one we have, it needs to be near 8 point, or it begins with an 8.2. Well, it looks like we've got an 8.2 in both. So let's write the 8.2 down, and it's 8.2 K. .2K, which is equal to 8.200, which since we're going to do some work with it, we'll work with it and then put the K back later. So let's get our color codes. 680, what is that going to be color code wise? Put that in the chat. And then as soon as you do that, put the other guy in there also. What do we get? Blue, gray, brown. And we said 10%, so it's silver. While we're here, we're going to write down what 10% is, just so we can. The other guy is 82. Gray, red, and then 2 zeros. Gray, red, red. And again, silver. And 10% of him is 820. Okay, so we can work on this piece of paper here just fine to do our math. And it's a little quicker than, well, not with my typing, it's not, but you get the idea. So we need 680 plus 68. This could be 748. In the other direction, $612. Okay, let's go down here. This could be 8200 plus 820, which is 9020. And it could be 8200 minus 820, which is 7380. Okay, so let's check these values. The voltage drop across the, I think was, collector was 12.9. So we're using 12.9 volts. Just writing that down so I remember it. So we can take 12.9 and divide it by 748. That equals to 17 milliamps. That's fine, within range. We can take 12.9 and divide it by 612. That gets a 21 milliamps. So it looks like our LED will be bright enough and it will be not burning anything up. While we're here, let's now multiply this again times 12.9. That gives us 270, or yeah, 270 milliwatts. So we obviously can't use an eighth, we can't use a quarter, we have to use a half watt. So our resistor is going to be 680, 10%. Let me write that just down over here somewhere so we remember it. And we said for the other guy down here, he also is going to be half watt and 10%. So we'll just write it down and keep track of the fact he is. Now we can do the other half if we choose to. What was the voltage for him? He was 3.3 volts. So let's do that. Let's take 3.3 divided by 9020. Stretch that out. Okay, so he's going to be in the micros also down low, but we don't really care. If we took these two numbers, you know, we go to 365 to the minus 4. Okay, and we got 3.6, or 3.7 to the, minus 4. If we took this number and we multiplied it back times 100, it's not going to exceed 17 milliamps, 21 milliamps. It's not going to even be in that ballpark. So it's safe for us with the voltages and things we did. Now, we could check these and get a little closer, but for the problems we're working, just to save time, once we've determined the value, the color code, that it's the same wattage, and it'll be the same tolerance, we're going to just leave it alone. So if we took this and multiplied it back times 100, you see we came up to the 36 milliamps. That's clearly bigger than any of these numbers. And so, of course, when we come down here, we're going to be using more current, and the more current, of course, would be bigger. So by just checking that number and multiplying it back, we got a number. So you should be able to do that, I guess. That would be a reasonable thing for you to do, is to check. And the wattage, of course, could be checked here as well. If we took our biggest number and divided it into 3.3, divided by 7380, it's going to equal that, which we take that and multiply it, back. We've got two things we could do here. One is times 3.3, which is going to take and say, okay, that's a very small number, so the wattage on that could have been 1/8 of a watt. However, since we bought 1/2, we'll buy another 1/2 over here. The other thing we could have done, let's see if I can cause that to happen here, is that we could have taken this and multiplied it times 100. And we'd have seen it was 44 milliwatts now, which guaranteed is bigger than any of those numbers, guaranteeing saturation. So you could do those as a check, and you'll probably impress me if you have a nice little table of all this stuff. So what we've decided is we know what values we need to get. If we were to be talking about the circuit and telling people what they needed to buy, you would be telling them to buy a 680 10% quarter-watt resistor. You'd also tell them you wanted to buy an 8.2K 10%. Actually, these were half-watt, weren't they? Half-watt resistor. And when they brought them to you, you would check that this was blue, gray, brown, silver, and you would check that this was gray, red, red, silver before you put them in. You also would find that once you got used to a particular manufacturer, that if a resistor came to you and it looked like that, you'd say, after experience, that's an 1/8 watt. You'd find that the resistor got a little bigger if it was a 1/4 watt, and you'd find that it got even bigger if it was a 1/2 watt, because you're dissipating heat. That's what's going on. Now, you mix brands and you go get another one, and you just get an arbitrary one out of a box, and it's this size. What wattage is that? You have no idea. So either you have to see the receipt in the box it came in with, or well, that's usually what I do, or you have to make sure you pick one that's nice and fat and put it in a place where there's not much current. I tend to buy things in bulk and leave them in the boxes until I use them. And then when I give them, like if I give them out to students, I tell you exactly what it is, and you should put it in an envelope or something that is labeled so you can find it again. Okay, so let's say we were doing another one of these. We don't have time to complete it in class, but I think next class, one of the problems we have is some people in the class have to get multiple time for tests and quizzes and things. So instead of a quiz or a test, what I would give you would be called a quest. So you don't get any extra time on it. But it's because once you do it, I give you the answer. And if you're still sitting there for another half hour working on a problem, while I'm giving out the answer, guess what? You always get it right. So it doesn't make any sense. So I think next time I'm going to give you one of these to work, possibly not as, it may not be as extensive, or it might, you just make sure you understand all the pieces of it. But here's a typical type of problem you might get. Where is this one here? It's over here. And the problem is it can't be treated like a, oh, I get extra time thing, because if you did, I'd be giving out the answer while you're working on it. Some things that might come. I might tell you that I want, and you're always going to, unless I tell you otherwise, always going to be working for the on condition, which means this battery is in the circuit as something other than 0. I might tell you the value for this, the value for this. I might give you a different value for the drop across the LED. I might give you a different range for the current. I might say that this is some other value other than 0, like perhaps 0.3 volts. I might give you a different value for beta. Maybe I'll say beta is 120. And you would still do all the solution, and the ultimate solution is tell me what resistor I need to go out and buy. And then you've made sure that it's safe, it won't burn up, it won't overheat, that it's got reasonable tolerances. Anybody have any questions about this? I don't believe that. Okay, well, my other class, they had a couple questions at the end of the session. They asked a couple things, like, for example, should they ever guess 0.3 on their own? And the answer is no. I'll tell you if that needs to be something other than 0 when you're doing a design. Should they always pick the middle number? Well, that's a common sense thing, is if you want maximum plus and minus, perhaps you want to pick the middle number to design with. Given resistors to pick from, let's say you have resistors located at these values along a number line, and the resistor you got sits right here. Should you ever pick this value rather than this value? And the answer is you might. Because once you work the problem and put in all the tolerances, this might exceed a range where it's not bright enough to be seen. Whereas if you came down here, it may get close to its maximum value, but it might still be able to be, have a range that's reasonable here. Can I create cases where neither will work? No, I'm going to create a case where the value you would have would work, which means it'll fall in both of their ranges. But picking the right one can become kind of artsy, crafty, depending on other things I might do in the circuit. So for now, if it's between two, you can probably pick either, but probably the better choice is pick the one you're closer to. So this is the sort of thing that will, be, maybe not everything changes. Maybe all I do is change beta. I won't change this value to be anything other than 0.7, although let's assume that I gave you a value of 0.7 here, and I said the other value here is 1 volt. If you knew there was 1 volt across that, we're not saturated. We're working like an amplifier. So if you knew this value and you knew this value, but not beta, you could tell me what beta was. If you knew this value and that value, you could tell me what that current was. If you knew this current and that beta, you could tell me what this value is. As long as it's not saturated, those three are related. If this was 1 volt and this did not divide into this beta number of times and I'd given you all three, you've got a broken transistor. Broken, I'm not going to spell that out. And that might be an answer sometime. Okay, I see the big hand is on the go out of here time. So if anybody has any questions, you can stick around for a couple of minutes after everybody else is gone. Otherwise, I will see you guys on Wednesday evening. If you come a little bit early, I might be able to give you some, I might be able, maybe if you come a little bit early, it'll be worth your time. I'll see you then. Be good.
Thank you. Have a good night, Professor.
You too. Bye-bye.
Thank you. Good night.